Now, this contour can be deformed, and we're going to get contributions from these little contours. And the path integral will give us this radial ordering. So it will give the contribution from all these pieces in this form. So I'm not going to write the dependence on the variables anymore, at least not for the ones that don't do anything interesting. So this contour, let's say there is z's much greater than 1, but all we need is that they enclose the w's. So here, this contour will be around the jth w. Okay, and the rest. But now, since everything is happening very, very close to the location of this operator, we can use the OPE of t and phi. But phi is a primary operator with some conformal dimension h. So we get something that looks like this, acting on the operator again. Okay? Therefore, you get that this thing is equal to the sum from J1 to n of these objects acting on the correlation function with only the primary operators. So we can put the integral outside. Okay. And now we use a standard argument that since that happens for any epsilon, then the equality has to happen at the level of the integrand. And therefore, we write a conformal Ward identity of the form Okay, so why are we doing this? Since you all know lecture 3 by heart, right? Because by now you had infinite time to study it. You remember that we discussed all this because we were trying to prove a theorem or at least a claim that we made at the time, right? And the claim had to do with descendants. Okay, so let me remind you the definition we had for descendants of operators. So we have, if you have the energy momentum tensor, the OPE with some field, let's choose the nth guy. Why not? But it works for any field. Well, in fact, maybe we should do it with. No, that's fine because then we're going to use this. So this is an example, just a field phi n, but it works for any field for the definition of the descendants. Remember, this field is a primary. So the definition was, well, you just expand this as a Lorentz expansion in z minus wn, and whatever the coefficients are the definition of the descendants of this field. So we have, so the first term of course, we'll start with a double pole, as we know, because this is a primary. And then it will continue, in principle, forever. And the objects that appear here are what we define as the descendants of the field. In particular, L0 is the field itself. Okay? Now, what can we do with this and with the conformal word identity? Well, we can combine the two things and do the following. So combine 1 in the limit when z goes to Wn and 2. Okay? Well, when you look at the expression 1, the conformal word identity, well, the first thing is that on the left-hand side, you can use this because now the field sits here with the nth field okay? And we can use the OPE that we describe here to write this as a sum from m equal to 0 to infinity of z minus Wn n minus 2. And what we get here are correlation functions of phi's and descendants. Okay? Now perhaps you remember what the result we wanted to prove was. The result was about the correlation functions that contain descendants of primary fields, right? You still don't remember what the claim was? Well, hopefully in the next step you will realize what the claim was.
The correlation function of the descendants is given by derivatives of the correlation.
Exactly. The correlation functions of any descendants are given by differential operators acting on the correlation functions of primary fields. That's a theorem that we wanted to prove. Okay? Then, as usual, we won't prove it in general. We will prove it only for a particular case and then assume that it's true in general, or let you prove it in general. But you see that now we're almost on our way there, right? And now you see what part of the theorem we're going to prove. We're going to prove the part of the theorem that relates to any number of primary fields and one particular descendant, okay? And that's the one we're going to prove is given by some differential operator acting on the correlation function of only primary fields. And we're almost there because we did that to the left-hand side, and now on the right-hand side, all we have to do is to take that and expand around z equals to Wn. So what we do is that we take, and here let me concentrate on descendants with m greater or equal than 2, okay? So when I do this, I don't have to worry. So what I'm going to do is to expand this and compare order by order with this. If I restrict myself to m greater or equal than 2, I can forget about the term j equals n and only concentrate on the terms j different from n. And these terms, you see why, right? Because the term j equals n will produce only a double pole and a simple pole, right? For m greater or equal than 2, I'm going to produce all the other terms, and those are the ones that I want to compare. So the first thing that I have to do when this is true is to write something like this. The first term that appears here, assuming that this is true, I'm going to write it as And don't worry, there is no way I'm going to do the whole calculation. I'm just showing a little bit. Okay, so we expand, assuming that this parameter is very small, and we get something like this. We also do it for the other one.
You mean that minus Wn on the right?
Here?
No, one below?
One below.
Yeah, there's
Here?
Z minus Wj should probably be Wn. We want to get.
Yes, you're right. It should be N. Thank you. That's the reason I won't attempt to do the calculation. Yeah, all we're doing is saying that this is a very small quantity rho and we're expanding. So there will be rho to the L. That's the expansion. So you're completely right. Thank you. Okay, and this one. Okay. Very good.
Can you repeat this? What does the meaning of the equation after we got descendants?
The equation, sorry?
Yeah, the equation 2.
The equation 2.
Yeah.
Oh, it is a definition. Of these guys.
Like definition how H minus M acts on Pn?
No, this is a definition. This is the definition of this object. Okay. Now that you mention it, of course, if we have this acting on any primary P, right, and we take the limit when W and W bar go to 0, this thing has to become dl. Okay. Okay. But now we're ready to compare both equations. And as I said, I won't attempt to do it in real time. But what we have is that the correlation function, so we can give it a name to this. This is phi n again, of something that involves a descendant is nothing but, well, you expand this, and clearly you're going to get some differential operator acting on the correlation function of the primaries. Now the trick is to sit with patience and match out the coefficients. And if you did that, you will get a differential operator that people call L sub k acting on the correlation function of the primary operators. Where this object is and you can see where each term is going to come from. Something like this will come from here. And this will come from the other kind of terms. And the minus sign has been taken into account by reversing these guys so that we don't have to keep track of the minus signs. Okay. Very good. So why are we bothering to do this? Well, yesterday we found that there are special conformal field theories that first have a finite number of primary fields, and second, the primary fields, when you studied the representation theory, you thought that they were very happily, that they were the only highest weights in their Wehrmann modulo, but then when you computed, you could check that there were hidden guys inside there. So the representation was reducible, so we have to get rid of those reducible guys. But those hidden highest weight guys were these null states, right? But these null states were made out of the original primary, right? By applying some L operators to it. So this new highest weight that was hidden in the representation was actually a descendant of one of these guys, okay? And then what we checked was that this guy was a null state, and all his descendants were also null states, orthogonal to everything else. So you can imagine that a field constructed out of that represents that state should be something that decouples from your theory completely. In other words, any correlation function that you have where you insert that guy should decouple, meaning should be zero, right? That's the meaning of a field decoupling from the theory. Now, that field is a descendant of the original primary, right? So you will have a correlation function of some primaries with that particular very smartly chosen descendant in there, right? That correlation function has to vanish, okay? But that's great, it has to vanish. But according to our little theorem, that correlation function has to be a differential operator acting on the correlation function of only the primaries. The primaries that you really want to study in your theory. So you have a correlation function that you know you want to calculate because it's made out of the primaries you want, acting on by some differential operator, and you know that this thing is a correlation function of something that contains this null state or this null operator, and it has to vanish. So what did you get? You got a differential equation for the object that you want to compute. So these null states are actually very powerful, and that's why you can do calculations in these theories. Okay, so we're done. That's it. We could simply say that you do this at home, and we can go home, and you can do it. But of course, things don't work out that way. No, so let's actually do it. I mean, it's actually exciting to see how the whole thing comes together and works. So let's apply this. So guess which theory we're going to choose. What's the central charge of the theory we're going to study? A half. Yeah. I mean, you could C equals 1 is actually the most complicated example. You're welcome to study it. But for the lecture, we could do it, but we have some finite time. So for the lecture, we're going to consider the simplest one, okay? C equals to a half. Okay, so let me remind you why this one was nice. Well, if you remember, we studied yesterday this plot of possible C's and H's. So C equals 1, that's why you said it, because you remember it was a very special point, right? That's right. That's why we're going to study that one. So C equals to a half was here. Then we had, if I'm able to draw it, we have something that goes here, and it goes there. Okay. We have another line that goes here. Of course, it met exactly on the line. And we have another one that goes from here. Here. We have another one. Wow, that's not going to work. Sorry. This one will not do what it has to do. That's going to be tricky. So this one has to go here, and this one has to go up here and up here. Okay? So these were the lines that we got by studying. So let me see. So this one was 1, 3. This one was 1,3. This one was 2,1. This was 1,1, of course. This one was 2,3, 1,2, and 2,2. Okay. And what are the possible values of h that we found? So we found h could be 0. H could be 1/16, and h could be a half. Okay. So in the simplest possible theory, we will have 3 primaries. Okay. This one is a trivial one. This one is the identity. But we will have 2 interesting primaries with conformal dimensions a 16th and a half. Okay? And this is what corresponded to the case m equals 3 in the discrete series. Okay. So that's the theory we want to consider. So again, we have the 3 possibilities. So let's write the values of P and Q for at least one of the representatives, because they, of course, meet with another line. So we could also write it with the other representatives. And let's give a name. So now what we want to do is to apply exactly what I said, okay, in the little speech, to a correlation function of this guy, of this theory. So you have to choose one of the fields. So let me choose phi to represent the field with conformal dimension 16th. Okay? Now we're going to assume, and we have to assume something to proceed. So in principle, the h bar part could be independent of this. But let's assume that the theory is left-right symmetric. Or in other words, that the holomorphic and the holomorphic part are the same. So this guy will also have conformal dimension h bar equal to a 16th. So it's a spin, is a field of a 0 spin. Okay? Remember, the spin was h minus h bar, so in this case it's 0. And it has delta equals to an 8th. Okay. So the goal for the next 10 minutes is to compute a correlation function for this guy. Okay? So we want to compute a 4-point correlation function. Well, this field is a primary. We know the conformal dimension, and therefore, we know that we can write down this correlation function as some factors that take care of the global conformal transformations and a function that depends on the cross ratio, on a single cross ratio. So let me write it down. So this is a bar part, and here is a function of the cross ratio well, there is something funny about this formula. which I thought I should mention before somebody asks. I'm giving you the chance to ask. Right? Well, what is funny is that if you use the formulas that we derived in the first lecture, you won't get exactly this, and it's easy to see why. The reason is that here there is a factor of the cross ratio sitting inside. And this is just because of historical conventions, okay? So this is not exactly what you will get, because there will be a factor of x here, but you can put it outside and redefine what we mean by f, okay? But that's just because, as I said, an accidental clash of notations. But it's completely irrelevant, okay? All right, so the goal is to compute this function. So what do we have to do? What will be step one? What's the correlation function we should study? So we want to study a correlation function that we know exactly what it gives, right? And the only things that we know what they give is when they give 0, right? Those are the simplest ones. So we should cook up a correlation function of a field such that the correlation function vanishes identically. And then, by some means, we can relate it to this object, okay? Well, in order to do that, we have to remember what the null state was. Sorry. Where our age is now 1/16. So yesterday we found that the null state was a particular combination of these operators acting on h, and for c equals to 1/2, we found, or you can find, that alpha is equal to -4/3. Okay. So this is the operator. This is the state we want to study. Or we want to find an operator that creates this state. And such an operator we're going to call chi. And we're going to insert it at W4 and W4 bar. Well, this operator, from the correspondence I mentioned, we have to be the descendant computed in this form of our original field phi. Okay? So in this theory, if we compute this correlation function, this is one correlation function we know how to compute. But now we can use the definition and write the same thing as using, let's write formula 3 here. So using 3 and 4, we can write this as L minus 2 minus 4/3 L minus 1 square acting on this correlation function. And that has to be equal to 0. Okay? Now, once again, we can sit down for a while and carry out this calculation, apply it to the formula that we have over there. Okay? So remember that this function is the function we wrote up there. So we have to take our differential operators and act on this and see what it looks like as a differential operator acting on f. Okay? So you all have 5 minutes to try it out. I think it takes more than 5 minutes, actually. So let's see. Yeah, can erase this. So instead of spending the 5 minutes, I can tell you what the differential equation is. The differential equation is something of the form, it's a differential equation for f that depends only on the cross ratio. So it's a differential equation that depends only on x. The order of the differential equation is 2, because we are at level 2. So much is known about differential equations of order 2, so we're lucky. And this is what you find. And that's the differential equation that has to be solved. Now, if you ask Mathematica to solve it, you will get something with arctans and complicated things and so on. But after you sit for a while, you can simplify and get what people found in the original papers. And what people found in the original papers is something much simpler than what Mathematica will give you straightforwardly. And it's something that looks like this. So there are, of course, 2 solutions. And let me denote them as y of x with plus minus, and they are of this form. Which is pretty nice, I think. Okay? So those are the possible solutions for this differential equation. Of course, we also have a similar differential equation for x bar, which the same function has to satisfy. And therefore, our function f has to be a linear combination of objects made out of the products of the 2 possible solutions, or of the 2 possible sets of solutions, one of the set with x and the other set with x bar. So the only notation I could find that was reasonably okay was something like this. Imagine that epsilon is a sign, and epsilon bar is also a sign. So you get something like some coefficients times the products of these guys. Okay? So that's pretty good. So we have reduced the whole problem to a problem of finding only 4 coefficients, which are just constants. Okay, so now we are going to use another physical input that will restrict what kind of theories we are describing. But that's fine. Given that we know the answer, right? So we know where we're going, we can do it with the benefit of hindsight a little bit. And then say that we want to think about our field phi is a local field. So we want its correlation functions to be single value. Okay? Now look at this thing. So this square root could pick up a monodromy, right? In fact, this function, as written, will in general pick up monodromies as we move x in the complex plane. But if we want this function to be single value, so I don't know how to call it, maybe we should call it G4. Let me call it F. Let's say F, or we want to be single value. And this would imply that only the combinations when we have the same signs will appear. Moreover, there could also be a flip here due to a branch. So only when we consider the symmetric combination of the two solutions, we'll get something that is single value. Okay? So this would imply that our function f is something that only depends on the modulus square of the two solutions. And there is a single unknown coefficient. Okay? So the final answer is that our correlation function that depends on wi's or wi bars is equal to, now we can put these things together. Let me put these two factors together, assuming that z and z bar are the conjugate of each other, and write this as and now you're going to see, well, not right now, but in 20 minutes, you're going to see why this convention was not only a historical accident, but there was a reason why it was useful. Oh, sorry, this is not a half, right? So what factor should that be? Should be a quarter times well, what we get here, right? So we get the norm of 1 plus 1 minus x, because the square root cancels, plus 1 minus square root of 1 minus x. All right. I think this is pretty good for the amount of work that, I mean, in general, computing a correlation function in a field theory exactly is impossible. So modulo the things we haven't done, like showing that this is actually that, I think is pretty good. Okay. I mean, I have to praise the result a little bit, because now we're going to forget about this for a little bit. Okay? And we should try to remember not to erase it, or I should try to remember. So if you see that I'm going to erase it, let me know. This is fine. And this is also fine, right? Nothing here. Okay. All right. So as I said, let's forget about what we have been doing so far, and let's go back to something we should have done before, but you guys actually discussed that in the previous weeks, which is the OPE. Okay? So if you remember, I also introduced a notation for the descendants, and I said that it was meant to confuse you. It was a joke, of course. It was meant to make our lives simple. And the notation was, if you have something like this, and now you see why the notation was invented. So this is a primary. So at the time, we only had one. So we said that it was LP of that number. But now we have this whole thing. So we're going to denote that as K bar, where these Ks are vectors, basically, made out of all the Ks here and all the Ks here. And they don't even have to have the same dimensionality. OK. Now, when we consider the OPE of two primaries, for simplicity, I'm going to put this primary at 0, 0. OK, so again, these two are primaries. So the claim that you have seen many times is that this OPE can be expressed as a linear combination of all the conformal families in your theory. And a conformal family is made out of a primary and all its descendants. That's why it's called a family. So we can write down this sum as a sum over all primaries okay? And then a sum over the possible descendants. We will have some coefficients which are going to be numbers and weights or dependencies on Z and Z bar that are completely determined by conformal transformations. And here, of course, we're going to get our excellent notation for the descendants, which you see, it was designed so that the whole thing could fit in a line. All right. Now, by now you know exactly what to do, right? So if you want to compute these numbers, what do you do? That's something you did. Probably we didn't discuss it, maybe, but yeah, probably we didn't. But you did it in previous weeks. So the trick would just be to sit down and compute 3-point correlation functions, right? Like you do every time you have something expanded in terms of a basis or something, you hit with one of the elements in the basis and you try to design an inner product so that you can project out everything else, right? Even if you cannot project it out, if you know what the inner product is, you will get a bunch of equations and then you can solve for the coefficients. Okay, so the same thing here. We're going to compute, or in principle, you should compute 3-point functions. Okay, what kind of 3-point functions? Well, 3-point functions involving these two fields. And any kind of descendants of any primaries in your theory. Okay? Well, but now we know that we should not be afraid of these guys, right? By our theorem, which is probably gone by now, but you know very well, this is a differential operator acting on, this is some differential operator O made out of all these L's acting on the correlation function of the primaries. But the correlation function of primaries is something that we wrote down in the first lecture, right? Of course, we wrote it down modulo a constant. There is a constant we didn't know, right? So we said that these correlation functions of primaries are all completely fixed by conformal invariance except for some constants that are called the structure constants of, well, let me assume that the notation, let's take the notation that if I don't write anything here, then you know what it means, right? So it's a correlation function of this, of only primaries. So it's the one that comes from only the primaries, okay? All right. Now, from this fact, and the fact that we're going to be solving linear equations for finding these CNs, clearly, if this thing is equal to 0, right, there is no chance we're going to get any of these things non-vanishing. Is that clear? I think it's pretty clear, right? So if this thing is 0, all these correlation functions are 0 because they are proportional to this. So there is no chance this is going to be non-zero. So this has to be proportional to this. And people like to denote the rest that contains the dependence on everything else as something like this. And these things are obtained by solving this system of equations. So they are only functions of C, C bar, and the conformal weights. Okay? So we're almost done with our detour. Having done that, we can now rewrite our OP as something of this form. Just as a sum over primaries with a structure constants the corresponding variation for the bars, and some object here, psi, that contains everything else. Okay? Everything else in the sum is going to appear in this function. Okay? And now the conclusion is that in a two-dimensional CFT, all we need are the conformal weights of primaries and the structure constants in order to define the theory. Okay, so for our simplest model here, we already have the conformal dimensions. So according to this definition, all we have to do is to compute the structure constants. Okay. So who is tired? Everybody, right? But I'm not tired. So we can just continue a little longer, right? The roll is only 5:30, almost 5. All right, so what else can we erase? So we can erase this. Okay. So let's go back to our example. Well, we have the 4-point function. It would be a pity if we didn't use it. I mean, we have the explicit form up to a constant. So how do you think we can use it? Any ideas? Part of the idea is to compute this. So we want to compute the constant, but the constant clearly is something that can be modified by the normalization of the fields, right? So somehow, once we normalize the 2-point function, the constant should be completely fixed. So let's assume from now on that the 2-point functions have been normalized to 1, okay? And therefore, the constant will be fixed by that. But how can we find these guys out of our spectacular answer?
There's an OP here. Do the OP for the first.
Exactly. Well, let's try to induce an OPE out of this 4-point function. So how do we do that? Well, just simply take W1 to go to W2 and W3 go to W4. So this is the same as sending x to 0. So we're sending the first and the second operator to get very close to each other, and the third and the fourth operator to be very, very close to each other. Okay. So let's see what happens to our formula in that limit. Well, the first thing is that from here, when x goes to 0, we get that this thing goes to 2. Of course, that's a leading order. We also want to expand this, so we will expand this 2 plus higher order terms. But the 2, I'm just mentioning the 2 because then we're going to have 2 times a. And the leading order then will come from this piece, and that piece will look like 1 over 1, 2 to the 4th, 3, 4 to the 4th. And if you put this on the computer and tell it to expand, you will find something that looks like this. Okay. Well, the first observation we can make comes from, of course, the OPEs of our field. Which has to be something of this form. Remember, these guys have h equals to h bar equals to 16th plus. So what are the fields we have? So we have this field phi, and in principle, we should give a notation also for the field with conformal dimension 1/2. So this would be a good time to do it. So the field with conformal dimension 1/2, 1/2, we're going to denote it for the lack of imagination, another phi, but it's a different one. This one is var phi. Okay. So let's denote it like that. So in the next order, what we're going to have? We're going to have the terms coming from 3 phi's times things that look like W12 to the minus 16th and W12 bar to the minus 16. This is coming from where? Well, look at the formula here. Okay? So we are looking at the terms with where the three guys are the same, right? So it's the C phi phi phi, regular phi, no bar phi. Okay? So we're getting 16 minus a 16 minus a 16. And that's how we got, for each one of these guys, we got a 16th. Now the next term, which would be something with two phi's, these ones here, and the new bar phi. What should the dependence on W's be? Well, again, we can use the same formula, right? But now this guy is a half. So this one will now be a half minus a 16th minus a 16th, and hopefully is 3/8, I think. So this guy should have a dependence. I mean, there might be other things here, but I'm only interested in the dependence on these things. So this guy should have a dependence of the form okay. So I'm looking at the dependence on W12. Okay. All right. Well, this thing is W12 to the minus 1/8, and this guy over here is W12 to the 3/4. All right, so now we go back and we look at our answer and ask, remember, this is only part of the answer, right? Because we're also doing the OPE of 3 and 4. But I'm hoping that with only this, I'll be able to read what I want. Okay? Remember, this is a 4-point function. We're taking these two fields together and two other fields together. We are supposed to do this for fields 1 and 2, and also for fields 3 and 4, and multiply everything. Okay? So the dependence on this thing, W12, if there was anything related to this, it would be to the minus 1/8, and we don't see anything here that has the same dependence. So the only possibility is that this object vanishes. Okay. Next, we see that according to our normalization of the 2-point functions, this coefficient has to be 1, and therefore we should get a 1 here because this is a 1 already. So this should be 1. And we conclude that if the 2-point functions are normalized, A has to be a half. Okay? And now when we expand this out, imagine that we are first doing one of the limits and the other one is still there. So we can expand this out and only concentrate on this. When we look at this, oh, probably that's what you were complaining about. These are supposed to be W's, right? Yes. Yeah. Nothing was making sense. That's why. Right. Okay. And these ones are also supposed to be W's.
Also, the C's are squared for some reason.
Why do you think the C's are square? That's a good question.
Well, you have two OPs and the same guy.
Right, we have the holomorphic and the anti-holomorphic part, yes.
Oh, yeah. So, yeah.
Okay, so if everything is working out right, then except the fact that I lost the other chalk. Well, it doesn't matter. So then this thing is supposed to be equal to a quarter, and we conclude that C phi phi bar phi is equal to a quarter. Sorry, how can it be a quarter? It's a half. All right.
Can you explain again why it's 12? Because
here you have Z and Z bar.
Let's see. Hmm. Well, let's see from the definition. Yeah, so you're right. So this thing should be linear indices, right?
They should be linear indices, and the quarter and the G4, that's coming from C squared, because there are two of these.
Yeah, that sounds more reasonable. Yeah, that must be the case then. So what is happening, as I think you're right, is that these are not squares. And the squares appear because we're doing the two OPs. And the second OP will also have this equal to 0, and it will have this guy, but now with 3, 4, and when they multiply, they better be a quarter. And therefore, we get this equals to a half. Yep, that makes more sense. Yes? Well, one of the reasons is that, do you remember what happens to this field when you compute descendants of the field? So we get these null states, right? And in principle, we could also have corrections here, okay? But our goal is only to compute these two objects. Well, these are the only two primaries that we can compute from here, okay? So the number of terms here, I mean, in principle, it could be infinite, but whatever they are, they can be computed from these ones. That was the theorem that we proved over there. So the only objective of this whole exercise was to compute these two guys, okay? So we computed them, and then in principle, one can compute any other part of information that we want in this theory. I mean, of course, this guy has an infinite number of descendants too, right? If you wish, the linear combination that is orthogonal to the null descendant that we found at level 2. Okay? So those things will also be there. Well, look at this formula, right? Well, maybe not this formula here, but look at the formula on top. Every time you're considering something that has a descendant, you increase the power here. So the most singular contribution will come from the first element in the family. So we are looking at the most singular contribution of each of them. One here and one here. And we also stop, that's why we're also stopping here. Okay? Very good. All right. So we're almost done. The reason is that we basically have solved this theory, except that, well, somebody should also sit down and compute what happens when we have the other field here and do the same exercise that we did, find the null state, the differential equation, find the 4-point correlation function, and then compute the structure constants. Assuming that you do that, we have solved this theory. Okay? The question is there any physical meaning to this theory? Well, the answer is the Ising model. At t equals to tc. Okay, so we will end the lectures by just giving the map of the things that we have computed and the things that we were computing in the Ising model. Okay. So I think that Jaume gave a little bit of a review of the Ising model, and you were taking statistical mechanics simultaneously to this course. So I'm sure you are experts in the Ising model, and probably you solved the Ising model in several ways in the lecture, in the statistical mechanics lectures. And you know that in statistical mechanics, we're looking for something called the critical exponents. And there are two different kinds of critical exponents that you can define. Critical exponents that are defined near Tc, and some that are defined at criticality. Okay? So to describe the ones that are near Tc, people use a parameter t that tells you how far you are from criticality. Now, what we did, the claim is that we are computing the Ising model at the critical point. So in principle, we don't have access to the ones that are near Tc, right? But again, I'm sure you can give me a lecture about the scaling hypothesis, right? So you all know that very well. And the scaling hypothesis tells you that everything, all the critical exponents, should be proportional, or should be, well, not proportional, should be computed from the correlation length. And then, if we can relate the correlation length somehow to these critical exponents, then we can compute everything just from things that we know at Tc. Okay? So, the correlation length is defined by this, okay? And at the critical temperature, we have that the correlation functions don't decay as fast as you have expected, but they decay with a power law governed by this critical exponent eta. Okay. Now you would say, well, how can this be related to the theory we found? We seem to have only one field or one object, which are the spins at each side. But it turns out that at the critical point in the continuum limit, you can also define another thing, which has the interpretation of the energy density, which is some sort of composite field of these two guys. And at the critical point, this correlation function also has some scaling behavior of this form. Okay? These are just funny definitions, also, I think, historical. For historical reasons, they are related like this. So in the continuum limit, it turns out that our sigmas would be described by a field phi, and our epsilon i's will be described by our field phi bar, or bar phi. Now imagine that you didn't know how to solve the Ising model, but you had a computer simulation and you could compute the exponents, the critical exponents to some accuracy, right? Then from there you will conclude that the 2-point function of z's, so now I'm using z's. You see how consistent the notation is along the lecture. Has to be something of the form eta. So if you only had a way of computing this thing in some approximation, you will find that eta is close to a quarter. Okay? Well, would that be good? Yes, you will conclude that it's exactly equal to a quarter. And the reason is that this thing has to be equal to 4 times the conformal dimension of the field phi. So it would match nicely with our proposal that this identification is correct and h is a 16th. Okay? Likewise, you will do it with the field phi. And you will find that this has to be something of this form. And you will find, after having made this identification, you will think that this guy should match the conformal dimension of the other field, but this guy is a half. And this would mean that the other critical exponent has to be 1, which would match your numerical calculations. Of course, in this particular example, we know how to solve the Ising model thanks to Onsager and then many other ways of solving it. So we know how to compute these things exactly. But if you didn't know, this would be one way of doing it. Okay? So last comment that I want to make about the identification is also something that is written in that you will find in many books. Which are the fusion rules coming from the OPEs. And the fusion rules are simply telling you what happens in the OPE of 2 primaries. What are the kinds of fields that can appear there? Then, of course, we can have, in this case, the identity. But we concluded from what we learned about the structure constants that you cannot have another phi here because we found that the structure constant phi, phi, phi was 0. So the only one that we can have here now is this other field. And it turns out that if you did the exercise to compute what happens to this one, you will find that this is just this. Of course, the 1 is not there because the 2-point function will be 0. The 2-point function of different conformal weights will be 0. And the last one is the simplest of all. It will just be the identity and its descendants. Okay? So that ends the identification with the Ising model. It ends the course, but let me just finish the whole story by telling you things that you could study in the future, or maybe, depending on, I don't know what it depends on, but if there was a CFD2 course, what would be the courses, what would be the topics that, that would be nice to cover? Well, it would be nice to, clearly the analytic continuation of this part would be the identification of other minimal models with the statistical systems. So in the, for future study, so you might want to identify other theories in the discrete series with known statistical models. Okay? Something else you can try is to study CFTs on a torus, okay? Or a Riemann surface of genus 1. So what we did in this course was to concentrate on the sphere. And here you will find that in order for the theory to depend only on the complex structure of the torus, it must have a property called modular invariance. Which imposes important constraints on the theory. Okay? Now you can have CFTs that, in addition to what we study, are such that they contain Lie group symmetries. Okay? You can add supersymmetry, you can add many things, you can study what are known as the West-Sumino Witte models, or WZW models. Or you could also go on and study the Langlands program. Okay? All right, I think this is a good point to stop. That's the end of the course.